Welcome back, geometry. I'm glad you made it. It's time for proofs. Don't hang up. Proofs are cool. Alright, so I'm going to show you how to work your way through a proof where we have to fill in some steps. So in triangle ABC, we are given that DE is parallel to AC. And we need to prove that BD over BA equals BE over BC. So we're trying to prove that the ratio of sides from one triangle to the next is a constant. Okie dokie. Well, in row 1, it's always a given statement. So, given. What are we given? We're given that DE is parallel to AC. So boom. 2. BA is a transversal that intersects two parallel lines. Okay, that makes sense. BA is a transversal that cuts two parallel lines. So now we're going to use that to say that angle BDE is congruent to angle BAC. Alright. And why can we say that? Because two parallel lines cut by a transversal, corresponding angles are congruent. Alright, now step 4. Angle B is congruent to angle B. So angle B is congruent to itself. What's it called when something equals itself or is congruent to itself? It is called the reflexive property. In this case, the reflexive property of congruence. An angle is congruent to itself. Now, for number 5, what could we possibly say if the reason we say it is the angle-angle similarity postulate? What does the angle-angle similarity postulate say? I think it says that two triangles that have two congruent angles are similar. Crazy. So it looks like triangle BDE has one angle congruent to triangle BAC. See, congruent angles here. And then angle B congruent to itself gives us that the triangles are similar. Triangle BDE, the little guy, is similar to triangle BAC. And then now, the last statement is always going to be the thing you're trying to prove. And why do we know that? Why do we know that BD over BA equals BE over BC? Because we have the side-side-side similarity postulate. If you have two similar triangles, then the sides, the ratios of the sides are constant, and the constant equals each other. So as long as we're doing sides that correspond, like BD over BA, that's the side between the two congruent angles, and then BE over BC, and that's the sides on the other side. As long as they're corresponding like that, then we're good. So in this situation, Adam, Paul, and Ben are standing along the shore looking for dolphins. Paul sees one, boom, straight out in front of him. And then we're going to use these triangles to try to prove the Pythagorean theorem. Okie dokie. Well, we're given a couple of things here. We're given that triangle ADC, so that's ADC is similar to ACB. So the little one is similar to the big one. And then we're given that BDC is similar to BCA. So the medium-sized one is also similar to the big one. So they're all similar to each other. And what is always the first statement? It is always part of, if not the entire, given statement. given triangle ADC is congruent to triangle ACB. And we're going to use that to get a ratio here, because the ratio of corresponding sides of similar triangles is a constant. So we need to figure out AC over what equals something over AC. Well, this might help us figure out what goes here and here. If you notice, AC, segment AC is B. And I got AC here and here, and I got B here and here. So whatever C is should go down here, and whatever E is should go up here. Well, E, I can see, it's AD. C is the side that is opposite angle C. So C is this whole length here. So that's segment AB. So E was AD and C is AB. And so now this we can just translate into this by rewriting statement 2 using the given segment labels. Alright, so statement 4, what do we say? Oh, here's a hint. Cross multiply statement 3. So B times B is B squared equals C times E. So B squared equals CE. Now where did this come from? Triangle BDC is similar to triangle BCA. That's weird. Why would they just have that there? Oh, hey, look. Given statement. Ding. Okay, so BC over BA. Let's see. BC, that is side A over BA. Okay, we're using the big triangle here. So we've got the long leg over the hypotenuse. So long leg over hypotenuse. Okay, so this is going to be my long leg, and this is going to be my hypotenuse. Well, BC is the hypotenuse of the medium triangle. So the long leg is BD. So BD is long leg over hypotenuse, so that means it's going to be BD right here. And now why can we say that? Well, this one is going to be the same reason as this one, because the ratio of corresponding sides of similar triangles is a constant. Alright, statement 7. What do I put? It's a mystery. Here's a hint. Rewrite statement 6 using given segment labels. Okay, so here's statement 6. So BC is A. So it's going to be A here and A there. BA is C. BA is C. And then BD is D. So I just need to substitute those in. So A over C equals D over A. Now, statement 8. How in the world did I possibly get A squared equals CD? Oh wait, maybe I cross multiplied statement 7. Alright, now look at statement 9. A squared plus B squared equals CD plus CE. Now where could that possibly come from? Well, if I look right up here, I got A squared equals CD, and that's like this part and this part. And then what's left? I got B squared equals CE, which looks like it came from here. So are we allowed to add 2 equations and get another equation? The answer is yes. You're definitely allowed to do that. It's like one of the most important things you do in algebra. Solve an equation. So we're going to add statements 4 and 8 together to get this statement. Then our reason for whatever we're going to say for step 10, our reason is factoring out C. Well, here is C. So if I factor out c, I would have d plus e left in parentheses. So lo and behold, statement number 10. Now, the reason for statement 11 is the segment addition postulate, and I kind of covered this before, that d plus e equals c. And now all we're going to do is we're going to use the substitution to substitute a c in here, and that would give us a squared plus b squared equals c squared. QED, end of story. I hope you had fun. Good luck on the test. I'll see you very soon. Bye-bye now.